why don't we just forget about the epsilon optimal for a second, right? Is it actually possible that we could get simultaneously, for example, a d squared and a d cubed just in the different set simultaneously? Forget about having lots of pairs. And that's sort of a little bit, so because I did a strict inequality, I could take epsilon to be delta squared, and that is answering this question. And that's actually something we considered quite a while ago. And in that situation, we get this sort of bound. So it's single exponential. And we, of course, there's some now dependence on the L is the number of polynomials, and K, I think I've never mentioned it. No, I did. It's just the maximum degree of the polynomials that we're considering. So, and I think I actually just restated here in a form that might be illuminating to some that this is actually saying, give some condition on how, as long as the density of the set you're considering is sufficiently large, then you're guaranteed to find a configuration, polynomial configuration of that form in the different set, right? And as long as you're considering, even in the case of a single polynomial, actually, as long as it's not a monomial, this is probably the best result, which is currently in the literature, although undoubtedly, I think we believe that much better results can be obtained. But it's, again, not really what I wanted to talk about today. What I thought would be amusing to talk about today a little bit is what one does in the general case of epsilon optimal bounds, where epsilon can be anything. And so we get the following ridiculously weak bound, but quantum bound nonetheless, that as long as it is n is greater than a tower of epsilon to the negative k e's or 2's or 3's or whatever. Right? So tower type bound, which scares the crap out of me. I don't know about you. Right, and I want to outline the argument, just actually sort of it's, at least I can write it down. So, yeah, I thought it'd be nice to just sort of outline how the argument goes, and you'll probably see that it's certainly not very optimal. I mean, it's very wasteful, and anyway, sort of a first attempt to try and answer this sort of question. Okay, so we use Fourier analysis. So on our group Zn. So I'm picking some eta now to be between 0 and 1. This is so the Fourier transform, as you can see, I've actually normalized it so that it's the Fourier coefficients of any function from z mod n to between negative 1 and 1 will necessarily take values between 0 and 1. And we say that it's eta uniform if all of the Fourier coefficients are less than eta. Right? So this, does that mean I've got 5 minutes? Yeah. So this is I should speed up a little bit. So this one can think of this as being sort of a measure of quasi-randomness. For example, if you look at a subset of the first n integers that we're considering A, and saying it's eta uniform is actually looking at this balance function, but it just means that all of its non-zero Fourier coefficients are small. Of course, the zeroth coefficient is just the density of the set. And in fact, if that's this balance function, or if the set is eta uniform, then that actually means that if you take your set and shift it and take the intersection, so if it was a random set, you would expect that to be delta squared n. We actually just talked about that, right? And in fact, it's very close to being that for almost all Ds. It's a very imprecise statement, but I wrote it down a little bit more precisely here. That's sort of a nice little exercise, actually. And it's essentially the same sort of thing as actually saying that if your set is eta uniform, then it also contains lots of additive quadruples. It's really sort of essentially the same statement. And so the idea here is well, we're interested in shifts, polynomial shifts. Okay, so our idea is sort of to establish the same sort of thing, but replacing the d with our polynomial, right? So if you think about it, if you had, so if some result of this was true, that you actually had almost optimal intersection for almost all d's, right? Then that would happen for each one of your polynomials. So there should be a d that works for all of them. That's sort of an idea. Right? So of course, so the idea is going to be to take a characteristic function of A and decompose it into the sum of two parts, where one part is is going to be uniform, right? So we need a sort of function version of what we just talked about, which is what I have here. So this just basically says if you take the convolution of two functions and one of them actually happens to be eta uniform, then it will be small for most values of d, right? So in other words, these will contribute error terms if I write the Cartesian function of a as f plus g. Any term involving the uniform part will be an error term. Okay, so how am I actually going to do that in 3 minutes? So I want to do this in such a way that, well, not only is the g going to be an error term, but the f is going to be a main term, right? And the way we do this is you define f to be the average of the Cartesian function of a over some Bohr set, which maybe I won't say too much about, but you can read it up there. And it turns out if you do that, then the g, which is necessarily just going to be 1a minus f, will actually be eta uniform, right? And you can sort of see the argument down here, and that really is just it. Right? So that's great. So that sort of explains at least how we initially make the decomposition so that one part is eta uniform. But is it actually true that their f is going to behave like a main term? Right? So that's the content of this lemma we've got down here. So if we look at f, we're really interested in f convolved with itself, evaluated at p of d. Let's just see what it is when y, if y is actually in this Bohr set, where the Bohr set is much smaller than this eta which we started with, then indeed, so f is, remember, the Cartesian function convolved with the Bohr set, or some sort of normalized version of the Cartesian function of the Bohr set. So because we picked this eta prime to be much smaller than eta, there's not going to be, things are going to be operating on sort of different scales. So in fact, the convolution really essentially collapses down to just being f of x squared, the sum of f of x squared, within an epsilon. If we pick our eta prime sufficiently small, it'll be within epsilon. And in a little Cauchy-Schwarz argument, you can then see that's actually greater than delta squared n, the factor that we wanted, right? So that's fine, right? As long as p of d is actually in that Bohr set, right? So then you naturally ask the question, well, for how many d's do we actually have pg of d in the Bohr set? Right? We want it to be there for all of the j's. So our Bohr set is defined in terms, so we start off with our initial collection of frequencies. So if we just label them xci, I actually want xci times pj of d over n, the distance to the closest integer of that to be less than eta for all i's and all j's. So this is a question, I'll just take 30 seconds. This is a question in simultaneous Diophantine approximation, which it turns out we were able to sort of dig it out as a theorem of R.C. Baker, that indeed a positive proportion of all the d's in play have this property, right? Unfortunately, not very big positive proportion. And the problem is the number of error terms and the number of optimal d's that we actually get don't match up. And then we've got to play a game to sort of fudge it so they actually do play up, and then this is where an arithmetic regularity lemma comes in, and we just do a sort of iterative argument which stops necessarily in a finite amount of time because the L2 mass grows with every step. It's sort of standard energy increment argument. So sorry I ran out of time, but I'll at least leave it up there for you to marvel at. Thanks very much.
There must be a finite field analog of these versions.
For the
So my question was, if you considered it in making a smaller tower, significantly smaller.
It's not completely obvious what the right finite field analog would be because we're looking at what's analog of a square difference. So, but we have been thinking about certain things in this direction, but not exactly this flavor, actually.